Good morning. So today I'm going to tell you about the models that power in-flight Wi-Fi. So as you heard, I work for Gogo Air, and if you've traveled on any of these airlines, you're probably familiar with our services, especially if you travel for business. Now, before I get into the modeling side and all the models that I'm going to talk about, what I really want to do is illustrate the business problem that the models are solving. And so to illustrate that business problem, I'm going to start with a little story. And it begins in what I'll call the good old days with our flagship technology, which is called Gogo ATG, or Gogo Air to Ground. So it's just what it sounds like. We mount little antennas on the belly of the aircraft. Those antennas talk to a network of terrestrial base stations, so just think cell towers. But instead of the antennas pointing down so your mobile devices can get service, they point up where all the commercial traffic is flying. And so, for the early 2000s and circa 2012, this was a really great network. We could provide peak data speeds of about 3.1 megabits per second, which for the time was really, really good. Just how good, I think, is illustrated well by this bar chart. So when you consider in 2010 that the average consumer used about, let's say, 10 megabytes of mobile data per day. This is on their phone on the ground, just regular data usage. If you compare that to what we could provide you in a 4-hour flight, this is realistic, not even based off our peak speed, it was more than adequate. So it was a great experience if you were flying during this time. Now, if you've flown more recently, and this isn't just us, this is most people, you might be more familiar with an experience like this. Okay, I'm hearing a lot of yeahs. So you guys know what I'm talking about. So this is what I'm going to call the dark ages. So we obviously saw the dark ages coming, and we started to develop a new technology to kind of solve this problem. So the explanation for the dark ages, I think, is illustrated well in this plot. So what you see in the blue chart is our, let's say, voracious consumption for mobile data. This is just with our handsets on the ground. It's not surprising when you see this, that it's just grown pretty much exponentially over the last decade. And if you've got young cousins like I do, they're constantly playing Fortnite or sending extremely high-resolution Snapchats every few seconds. So this just slams our network. And so what you're looking at here is a plot of average monthly data usage in the United States. That's in blue. And the equivalent capacity of our ATG network in red. Now, we had other technologies to kind of keep up with this trend, but this does a really good job of illustrating why you might have had a bad experience recently. So to bring us out of the dark ages, we developed a new technology. This is a satellite technology, and this is kind of the focus of my talk today. So we literally raised the bar here to capacity that looks like that with the possibility to more than double it. So we call this technology our 2KU. KU because it connects to the KU band of satellites in geostationary orbit. 2 because there's 2 antennas. So instead of mounting the antennas on the bottom, we mount them on the top. So that's actually the focus of my talk today. This is predictive maintenance around these antennas. So the antennas talk to the satellites, which go down to teleports and give you the regular internet that you're used to. And so these really high speeds come at a cost. And the cost is loading on a bunch of really high-tech, lots of airborne hardware to make this work. So we've got our onboard servers, we've got really high-speed modems, satellite controllers that contain a bunch of basically RF amplification circuits. So really a lot of technology just to bring you really high-speed internet. And so importantly, these are the new antennas that are mounted on the top. And there's 2 of them, one for transmit and one for receive. So this is the focus of today. So I spent some time in Atlanta with one of our airline partners, and I got to see the installation of these antennas. And they're really cool. They're huge. They're what we call a phased array antenna. And what it consists of is 4 platters. And these platters create a beam that points to the satellite that sends your data back and forth. So importantly, so this is all predictive maintenance. These are all the models I'm going to talk about today. Importantly, these 4 platters all spin and rotate independently. And when they do that, that allows the beam to track the satellite despite the movements of the aircraft. So when the aircraft pitches, rolls, banks, yaws, et cetera, these antennas are spinning in the Sparing Raceway. This is key here. These things are spinning, and it allows the beam to keep tracking the satellite. So that's the idea. And it works really well, and it's extremely fast. So because there's a lot of technology in here, it's important that we protect it. And we protect it with this thing called a radome. It's basically a cover. And this protects the antennas from 100-degree temperature swings, 500-mile-an-hour winds. It's kind of a harsh environment. We have these adapter plates and these fairings, so all this stuff kind of gets connected together, and it sits on top of the aircraft, and it looks just like that. So when we started to roll out this technology, it was like late 2016, early 2017. And these antennas were supposed to last something on the order of years. And what we found is that they were lasting something on the order of months. And a lot of them in particular we found were being replaced in the wintertime. So what we learned is that de-icing fluid was the likely culprit. So if you've ever flown in the winter, you might have noticed that they're kind of power washing the aircraft. And that's deicing fluid. Basically, it breaks up ice and snow off the aircraft so things don't freeze, control surfaces don't freeze, and you can fly safely. So what we found is that after a bunch of exposures, this really high-pressure deicing fluid gets in between the cracks in the radome and the adapter plate, and it actually seeps into the antenna. And once it gets into that bearing raceway, the platters don't really spin as easily. And so in our defense, we had been told kind of that most of the de-icing operations mostly just focus on the wings, the control surfaces of the aircraft. They don't really mess with the top of the fuselage because it's smooth and stuff just slides off. As you can see in this picture, the real world's a lot more complicated. So this was a kind of an existential threat for our business because all of our airline partners were disappointed in us at the time because we'd promised to provide this really high-speed internet, but whenever the aircraft would get de-iced enough times, it would stop working. So we really needed to figure this out. And they came to us with this problem, and they said, "Okay, data science team, we know that there's this problem. We want to be able to have some predictive power, or at least some insight into what's going on. How healthy are these antennas? When do we need to know about when we can replace them? How can data really help with this problem?" And so we sat down and we thought, and one of the first questions I asked was, why don't we just wait until a bad flight or two happens and people are upset with us, and then we go after the aircraft. And the way we know is we measure this thing called availability. It's just basically the fraction of successful pings that get sent from the aircraft to the ground. And so why don't we just wait until we find an aircraft with poor availability and then go check the antenna? And the response I got was really interesting. So for our airline partners to make money operating on, let's say, a long-haul route with a wide-body aircraft, those aircraft need to spend more of their useful life flying in the air than sitting on the ground, which is pretty amazing if you think about it. And because of that, you can think how that translates to the number of available maintenance opportunities, especially maintenance opportunities to do something as trivial as work on the airplane's Wi-Fi. So it's imperative that we execute on point, and we get our maintenance right, and we get it right the first time. So having as much insight and predictive power into this is really great. So we'd met with some hardware engineering teams, and they had kind of told us that there's these logs, and these logs contain this value called motor current. They contain a bunch of other things too, but they thought that maybe the motor current would give us some insight into the status of the antenna, because the hope was that the more motor current that the antenna needs to spin, the more friction that's building up in the raceway, and your antenna is beginning to degrade. Now, a lot of folks, both in our company and with the vendor, had looked at this, and they hadn't really seen a lot of evidence that this was the case. We kind of knew or had hoped that that was the case, but nobody was really sure. So we were kind of going into the dark. So a little bit about the data. So data is generated on the aircraft at a rate of about 2.4 hertz. That's one record every 400 milliseconds. From there, it's bundled up and sent up to the satellite, which goes down to the teleport through the backhaul internet infrastructure. It winds up in our data centers here in Chicago. And then from there, it gets parsed and streamed up to our data warehouse. So the vast majority of these logs, the average delay between the moment that record was created on the aircraft and the moment it appears as like a queryable row in our data warehouse is about 1.2 hours. So that's really pretty good. Not amazing by today's standards, but perfectly adequate for what we needed to do. Now, each day at the time, this was about a year ago, we had about 15 gigs worth of antenna data. And that basically made up a kind of a small fraction of the total number of airborne logs. So the total number of airborne logs, which we needed to kind of join up with the antenna data, was about 4 terabytes per day compressed. So kind of big data, but not huge data by any means or by today's standards. So this was this is kind of what we were dealing with in terms of our data landscape. Now, there's a small caveat to all this, and the small caveat is that this antenna data, specifically the data that contains the motor currents, was encrypted by the vendor. So when people needed to start looking at this, they had to go through this complicated manual process of sending the data to the vendor. They'd decrypt it and send it back to us, and so the extent that anyone could look at the data wasn't really big data. It was just like a handful, maybe 20 or 30 tails with relatively short time frames. And so when we looked at the data, so this is into the EDA portion now. When we looked at the data, it looked like this. So we just loaded it up into our favorite BI tool, and this is what the raw data actually looked like. Now, there was a replacement right here in June, kind of in the middle. Let's see if the laser pointer works. There was a replacement right around here. So old antenna to the left, new antenna to the right. If you guys can see a difference between the left and the right, that's great. You should probably take my job, but nobody else could. And so we sorted through this again and again. And, me and my boss at the time were kind of going through these examples, and we weren't really having much luck. And then I remember really well, I was brown line into work, and it was the morning, and I'm checking my emails, and I get an email from my boss with the subject line, "It's there." Now my interest was really peaked. So we were experimenting with taking different averages and stuff. different daily aggregations, aggregating along different timescales to try and see this signal or this degradation. And so once we had seen this, so what you're looking at here is a plot of an antenna's motor current as a function of time. And he had taken, I think, daily or hourly aggregation. Why we didn't see this with the other examples is a long story, but it basically goes down to the fact that we didn't really have that big of data to begin with. We only had a small handful of examples to look at. But what you see here is that the antenna current's kind of going up over time. A replacement happens here. And then you can see that this is the new antenna, and the currents are, really, really low and consistent, and there's really good availability over here. So once we knew this, we had a sense for the time scale that this occurred on, and it kind of confirmed all of our intuitions over what we'd hoped it looked like. So the next step then was to start a little more, filtering and stuff. So what you're seeing is the same data on the right and left, but we applied some filtering. And so as we met more and more with the hardware engineering teams, we got a better intuition. So I mentioned before that as the aircraft banks and turns and pitches and rolls, the system sends really high pulses of motor current to keep those antennas keeping up with the motion of the aircraft. And unfortunately, those really high pulses can look just like a truly degrading antenna. So you get high currents from two sources, bad antennas and aircraft maneuvers. So once we kind of figured out how to filter out those aircraft maneuvers, we could transform our data from looking like this over here to something like this over here. So the trend on the right, I would say, is a lot more clear than the trend on the left. And a replacement happened right here. So you can see the differences between here and here. I'd say it's hopefully abundantly clear. Now, this was nice, and we'd been able to reduce our data a little bit, but the problem was we still had really, really heavy data. I don't know if you've ever tried to load several gigabytes worth of data into a dashboarding tool or even matplotlib, but if you try to do it in a plot and expect it to go fast, or if you want to make 100 or 200 plots or 100,000 plots, it takes a while. So what we were able to do was reduce the data by a factor of about 100,000 and just take daily aggregations. So this is the filtering that I'm talking about, and the filtering allowed us to take these aggregations. And so you can see in the example here on the left, in example 1, I'm labeling it, this is motor current as a function of time, and you can see the difference in the trend between the filtered data and the unfiltered data. Here, if you want to run some regression on this, it's really easy, and you can see the antenna replacement happens here. So once we were able to apply this filtering, we could look at this data at scale. We could scale up over our entire fleet of 500 aircraft, any time range we wanted to see, and we could do it quickly and easily. And we could see all these examples, and what became clear to us pretty much immediately as soon as we could do this is that we really needed a twofold approach to our modeling. So on the left, obviously, that screams regression. The right, if you try to run some regression over any reasonable window, you're going to be kind of limited over here. And if you fit this is a 2-week window right here, it's actually going to show a downward sloping trend. That's obviously not what you want. So here you want a classification, basically telling you that high motor currents are bad. Not so bad. Now that I'm going to transition into the modeling start. So for the classification, there's a lot of different ways to approach this, and we'd proven that gradient boosted tree ensembles work. There were a lot of different ways, but what we ended up settling on was GMM. And what's nice about the GMM is it's actually rather straightforward and simple, especially if we're going to talk about interpretability. So the idea is that you get a bunch of healthy antennas. You build some features, and I'll talk about the features in a minute, but you get their features, and you make this multi-dimensional Gaussian in the space of the features, and it's a mixture of Gaussians, actually, and now you've got a really accurate picture distribution-wise of what a healthy antenna should look like. All that remains to do then is go through all of anything you want to test out there and see, okay, how consistent, where does this fall in my mixture of Gaussian distributions? If it falls out in a tail, it's probably not consistent with a healthy antenna. If it falls somewhere in a fat peak, it's probably really consistent with a healthy antenna. So what we did is we looked at not just the mean, so the daily aggregation of the mean, all the different percentiles, and we had to do that for each of the 4 platters because I mentioned there's 4 platters per antenna, and we create 2 models per antenna. We also do this for different software versions, but I won't get into that. But what's nice about taking these percentiles is the model not only knows about the mean, but it also has a lot of information about the shapes of the distributions, which is really important. So we did this again for healthy antennas. We took about 230 or so healthy antennas whose average availability for 1 month was greater than 98%. 98%, the reason we chose that is because that's what we sign on with our airline partners and guarantee we'll provide in our contract. So we know to a high degree of confidence that these antennas are really healthy. So that gives us about 7,000 unique examples to build this distribution. So we're off and running with this, and we've got a lot of stats. life is good. So if you've ever messed with mixture models before, one key hyperparameter that you need to tune is the number of Gaussians that are going to go into that mixture. So for this, we selected 3. And the way we selected 3 was part by intuition and partially kind of empirically. And if you notice and you look at some of the percentiles, you can see these percentile distributions in blue. Those are for the healthy antennas. The red distributions are for the failing antennas. But if you look at the blue, what you notice is at a minimum, they're bimodal. And if you look really closely, you can see that there's kind of a nice long tail out here. So at a minimum, we should be thinking about k equals 2 to 3, and we tested higher values, but we found that the performance gains from increasing the k value didn't really buy us much. So we just stuck with the simplest possible thing that works and got on with our lives. So the whole idea of this is to be able to classify antennas and communicate that information to the airline maintenance teams to know which aircraft to go after and which antennas to replace. Now, you can use the GMM for a lot of different things, but one of the outputs you can ask from it is an output of log probability. So if you're going to throw around log probabilities to people that aren't data scientists, I don't recommend that. And so what we did is we transformed that log probability into a metric we call antenna current health, which is bounded between 0 and 1. It's basically the degree of normality of the daily motor currents value. So 1 is perfectly consistent with a healthy antenna falling somewhere in the peak or near the peak of the Gaussian, 0 being completely incompatible with a healthy antenna. So this is where the zeros are where your unhealthy antennas end up, basically. And so we tuned our sigmoid function as the midpoint being corresponding to a p-value that was consistent with about 2.5%. And so in terms of what kind of working point we're going to use to send warnings and label an antenna as bad, we use this rock curve to tell us that. And these antennas, I don't know if I mentioned, they're really expensive. They're about $70,000 a piece, and there's 2 of them, not to mention all of the cost associated with taking an aircraft out of service just to work on it. So for all those reasons, we really can't tolerate any false positive rate. So we tuned it to effectively have a 0 false positive rate, so 1 mistakenly fired out of about 234, so not bad. We do pay a small price in terms of true positive rate, but that's actually balanced out with the power that we get from the regression model. So before I talk about the regression model, this is what the output looks like, so a little more interpretable. On the upper plot, you see the health of the RX antenna. Again, 1 is consistent with healthy, 0 is consistent with unhealthy. You can see the degradation right here. The x-axis is time. We do the same thing for the TX antenna down below. So this is just a screenshot from one of our dashboards. So as you can see, it's a little bit noisy, but it's really sensitive, which is nice. And so we can balance out a little bit of that sensitivity with the regression model. So again, what you're looking at is a plot of motor current as a function of time. And what we saw is that there tends to be a specific point in motor current values, as measured in milliamps, where the system availability typically gets impacted. And so all that was left for us to do is just kind of predict, based on the slope of our regression, how much time do we have until we hit this point. And we can output a number for you in days. And that's basically the idea. So as you can see here, this is kind of raw motor current values. I've taken a different aggregation. It's going up. When it gets to around 0.3 of an amp, that's when we know the availability is really impacted, and that's when we really need to take action. And so you can see this is how the regression works. So how we tune those working points was, again, to basically have a 0% false positive rate. So if you just look at the distribution on the left, in red you see healthy antennas, in orange you see failing antennas. This is a distribution of motor current values. We basically picked our working point here to have a 0% false positive rate. So above this threshold, you're not going to see any healthy antennas, basically. So that's the idea behind the regression. Now, in terms of performance, this is our training set. This was the first iteration we used. I won't go into too much detail here. But in terms of performance, we see pretty solid performance. As it turns out, healthy antennas don't often show an upward trend for more than a few days, which is nice. So we have a really nice false positive rate and a decent efficiency at the same time. So now I've talked about a little bit of the technical nature. You guys are all technical people, so you can bug me later if you have technical questions. But I want to talk about what I would say is the most important part of this talk, and where I learned the most, which is the people, and getting the people to buy into the model. So we had made this really great dashboard, and I don't make it very big for a reason here. But we had made this really great dashboard, and we felt that we were so smart, and we had met with leadership and the maintenance teams, and everybody was saying, great work, nice job. But I still had people coming to my desk asking me, can you tell me if this antenna's bad or not? And I was like, well, I don't understand. I gave all these presentations. I shared this link with the dashboard. Like, why are you asking me? It's all right here. It's clear. It's night and day. So what I realized pretty quickly is that nobody cares. So one of the big takeaways that I learned as kind of a rookie data scientist at the time was that when you're designing your interface, whoever's consuming the output of your model, you need to take those folks' input seriously, and you need to design that input with them in mind, and pretty much design it with them hand in hand. So I found this to be kind of a game changer. So once we started taking their advice more and more, they were a lot more receptive to listening to what our model had to say. Not only that, what I found is that if you can display some of the data that the model is using to make its decisions right next to the model output, that builds a lot of trust in the model. If you just show them something like this, and your job is to replace $70,000 antennas, and you're making a $70,000 decision, and this is all you have to look at, and that's your job, you're probably not going to trust this. But if I can show you the data that the model is using to make that decision, this is kind of going back to interpretability here, if you can see the motor currents rising up over time, that builds a lot of trust in what the model is saying. So once we had started to do this, we started to gain a little bit of traction. And not long after that, we started to automate things. And so our first attempt at automating things was with a little cron job running a Python script that sent out emails with links to the dashboard. So every day, everybody that wanted to be on our email chain, which actually grew to be pretty big after a while, got a link with all the aircraft that we could find and the antennas and links to the dashboard, and everybody could see. So that was useful, and that was the status quo for maybe the first several months. And it wasn't long after that we plugged in the model output to a ServiceNow API. So if you're not familiar with ServiceNow, it's the tool that we use to track all of our maintenance that goes on across all of our different airline partners and fleets. So the moment an aircraft needs to get worked on, all of that work is traceable in a ServiceNow ticket. And so now what our model does is it just opens a ServiceNow ticket directly. It gives you a little blurb here about the link to the dashboard, why we thought it was bad, and then that you can contact the data science team if you have more questions. So this is what we do today. Now, this was really nice, and it gave us a lot of insight into how this worked. And more importantly, what it did is it got everybody kind of on the same page that high motor currents really are predicting bad antennas. And so I could show you system availability or revenue, and I'd love to show that, but I think my colleagues across the street in the legal department would be a little disappointed, so I won't show you that. But I will show you his Net Promoter Score with one of our airline partners, and I think it's a decent proxy. So Net Promoter Score you can kind of think of as a likelihood of how probable it is that someone that's using your product or service is going to recommend it to others. And it varies pretty widely by industry, with internet service providers and wireless carriers kind of dragging everybody down. Maybe not surprising if you think about your experience with your internet service provider. So in terms of Net Promoter Score, where should we go? We're kind of this weird chimera of wireless carriers and ISPs. Our Net Promoter Score ideally should be somewhere in the teens, and that's just to be average. So this is what our Net Promoter Score looks like. The red plot, this is Net Promoter Score as a function of time. The red plot is for our 2KU technology. And at the time, we were kind of right around 0 or single digits, so not very good, well below the industry average. Since those models have been deployed, and since we've gotten smarter about how we use our software on this aircraft to kind of overcome this friction in the raceway, which is informed by the knowledge from the motor currents, we've improved this really significantly. And so on the right-hand side, this is where we are today, 25. Our industry average, hand waving should be somewhere in the mid-teens. So tracking 10 points better than where we really should be for our industry. So that's our Net Promoter Score, and that's all. Thank you.
Awesome presentation. Maybe this is a silly question. Why not just fix the housing around the antennas in the first place?
That's exactly what we did.
Okay.
But we didn't know which aircraft to go about doing it, and we needed to test things. And there's a really, in our industry, unfortunately, there's kind of a long delay around any action you take because it has to get approved by the FAA. So what we actually ended up doing was sealing up the radomes because we realized deicing fluid really is getting in here, and the motor currents, and we had it down to a science, or we have it down to a science. And the solution we eventually deployed was, let's see if I can go back here. You guys are going to laugh, but I think the most simple solutions are often the best. Let's see here, where is it? yeah, so what we ended up doing was applying the equivalent of your bathtub caulk. It's a little more fancy, but it's called an RTV sealant. And we applied that basically to these gaps in this radome and adapter plate. And what we were also able to do from this was get a lot smarter about when we get installed on a new aircraft type, all of this adapter, fairing, all this stuff needs to be designed specifically for that fuselage, for that aircraft type. And so now in the tests, we can look right away and know instantly, is this a good design? Is this going to let stuff through? Or can we be smarter about not letting stuff in? So the bathtub caulk for sure was a big part of the solution, and being smarter about the new aircraft we're getting installed on also helped with that.
Great presentation. Can you describe how many, what is your sample size for your data? Is it 230 odd or?
No, it's actually, this was initially when we first deployed it. Now I think it's in the, well, it depends on the model that we're talking about, but I would say it's in the thousands. So in terms of the statistics that populate that GMM, I would say it's easily into the tens of thousands at this point.
But the actual antennas are in 200? Or?
Oh, the actual number of aircraft installed. So when we
Right.
started this, there were about 400-ish, give or take, flying on any given day. Today, I want to say there's around 1,500 installed, and it's only going up with about 1,200 flying per day.
So you're making a prediction on each of those 1,500?
Every day, yeah.
Every day, okay.
Exactly.
Okay, and how many features, again, you ballpark estimate, are you using?
So for the GMF, so for the regression, we just use the straight up filtered out motor currents. For the GMM, we have 4 platters in each antenna, and we measure the currents for each of those. So we take 5 unique features times 4 platters, so that's 20 inputs. And we do this, we have separate models for the TX antenna and the RX antenna because the way the software controls it is a little bit different. But the idea is the same. So 20 features going into the GMM.
And final question, how are the end users actually using it? You're making a prediction, you're saying this antenna is going to fail, right? So
Yeah.
there's a time from the time you're making a prediction to the actual repair. How does that work?
Yeah, so I didn't really get into that so much, but we actually do an ensemble of both the GMM and the regression, and we actually add a little more information about the log files that involves the availability. So before we even open a ServiceNow ticket, I don't know why I'm trying to show you an image of a ServiceNow ticket, but before we even open up a ServiceNow ticket, we require that the aircraft be flying well below our SLA, so it's got to have poor availability, and either the GMM or the regression needs to have fired on it. And so that's kind of how we do it. So we initially open up a ticket. All the maintenance folks get an email that this ticket's been opened, and they can go to the links to see the currents themselves and take action from there. I think there's one more. Do we have time for one more? So the question is, how does all of the data come from each airplane separately? Yeah, they're absolutely analyzed separately. But all of it comes in on the same stream to our data center, and then all of it, we don't care about the aircraft at all. As soon as it comes in, it gets uploaded and pushed to our data warehouse. We're really smart about the way we send those log files up because we're leasing the satellite bandwidth. So we want to be not sending really heavy log files across the satellite. So we have another modem on the aircraft called the terrestrial modem, and there we're basically sending it across an air-to-ground network. And so the really heavy log files get sent across there, but we compress everything and stream it up. Like the really sensitive stuff gets sent across the satellite link. We use different protocols, so we have different tunnels that will route browser traffic. So if you're sitting surfing Facebook or downloading a presentation, you'll be going across one tunnel, and the tunnel that we reserve for the log files is a separate tunnel. Edge computing is, we'd like to get there, and it's going to require us to work a little more closely with the vendors and the software teams when they design the next versions to get something like this into that. But the software right now is changing so quickly that I don't think we're quite there at the time. But that's absolutely the direction we're moving in.
Okay, thank you very much.